Consider a heavy wooden swing on a playground. If you pull it back and release it, it settles into a very specific rhythmic pace. That inherent rhythm is its natural oscillating frequency. If you were to walk up to that moving swing and shove it at random intervals, you wouldn't accomplish much. Sometimes you'd hit it while it's coming toward you, sometimes while it's moving away. You'd kill its momentum. But if you wait and apply a push at the exact right moment, matching the swing's inherent rhythm, the results compound. With very little effort, the amplitude of the swing grows massive. This is resonance. It occurs when an external driving force perfectly matches a system's natural frequency, producing the maximum possible response. We can map this same behavior onto an electrical scale using an LCR series circuit. This is a closed loop containing three basic components: an inductor, L, a capacitor, C, and a resistor, R. Instead of a person pushing a swing, this circuit is driven by an alternating current voltage source. This source drives electrons back and forth at a specific angular frequency, which is essentially the speed of the current cycles. Just like that playground swing, this specific loop of components has its own hidden natural rhythm. Finding this circuit's resonant frequency is the only way to achieve its maximum current response. But to get there, we have to navigate a mathematical tug-of-war happening inside the components themselves. The primary roadblock in any AC circuit is called impedance. Impedance is the total combined opposition to the alternating current flowing through the loop. The inductor and the capacitor fight that current in opposite ways. This opposition is called reactance, and we can map it against the frequency of the circuit. As the AC frequency increases, the inductive reactance slopes upward linearly. Meanwhile, the capacitive reactance swoops downward toward the bottom of the graph. Eventually, these two lines intercept. This is the exact moment where the varying reactances become perfectly equal. Because voltages across an inductor and a capacitor are entirely out of phase with one another, reaching this point of equality means they mathematically cancel each other out. This moment of cancellation strips away all reactance, leaving the circuit unhindered by anything except its base resistance. This balance point is the resonant frequency. It is defined by the formula: omega naught equals 1 over the square root of inductance times capacitance. At this specific frequency, total impedance reaches its absolute minimum, becoming exactly equal to the base resistance of the circuit. With the electrical roadblocks minimized, the amplitude of the current inside the loop is allowed to surge to its absolute maximum. If we plot current amplitude against frequency, we see a clear bell curve. The current rises as it approaches the resonant frequency, peaks sharply at the center, and then falls off as the frequency continues to rise. The height of that peak is controlled by the resistance. A lower resistance of 100 ohms creates a sharp, massive spike, while a higher resistance of 200 ohms creates a much flatter peak. This mathematical peak, where the current is at its strongest, is the exact electrical equivalent of pushing that playground swing at the perfect moment. To see the value of this math, look at this vintage radio. The air around it is a chaotic soup of thousands of overlapping electromagnetic frequencies, all broadcasting at the same time. How does a box of wires isolate one song out of all that invisible noise? Behind that tuning dial is a variable capacitor connected directly into an LCR circuit. Turning the dial physically changes the capacitance. This shifts the circuit's resonant frequency across the spectrum, essentially hunting for a specific station's broadcast frequency. When the circuit's resonant frequency matches the incoming station's frequency, that signal's current spikes to the maximum. It overpowers the surrounding noise to deliver clear audio. If you are studying this for an exam, remember 3 rules. First, resonance is impossible without both an inductor and a capacitor present to cancel each other out. Second, the mathematical trigger happens when capacitive reactance equals inductive reactance, forcing total impedance to equal base resistance. Third, the physical result is that the current amplitude achieves its absolute maximum value. By learning to balance these opposing electrical forces, we gained the ability to pluck a single signal from the air, connecting textbook physics to the modern world.